Yes. Yeah. All right, so any questions? So you have an ODP up. The ODP is simply writing a function called fib that finds the nth Fibonacci number. And you're welcome to do this any way that you like. The most straightforward way is probably iterative. And remember our definition. So f of 0 is 1, f of 1 is 1, f of 2 is 2, f of 3 is 3, f of 4 is 5, and so on. And the general formula for f of n is just f of n minus 1 plus f of n minus 2, where n is bigger than or equal to 2. So these are your base cases. And then for any number bigger than 1, you can just take the two previous values of f and add them together. Now you can code this recursively, but it's a nightmare. The largest number I'm testing with is 45, and 45 will take many, many minutes to answer this question recursively. If we get through dynamic programming today, you can do it with dynamic programming more efficiently, but you can also just do this iteratively, right? So it's a basic simple for loop. At each point, you take the two previous values and add them together. So you just need to keep track of the previous number and the previous number before that. Add them together, that's your current number, and then your current number from before becomes your previous, and the number before that comes the previous two before. It's not hard, but it's more than 5 minutes if you've never done this before. So don't start at 7:45 in the morning, and I know who you are who does that, because I get timestamps on your logs. So leave yourself some time. If you've never coded this up, it's an enlightening exercise to do. It's not a lot of lines of code. It's about 5 or 6 lines once you get it nailed. But it takes some thought to figure out how to line those things up. But it's really just kind of like what we do when we march through a linked list, just keeping track of current and previous. But you got to keep track of two previous in this case. So, but when you get it right, it jumps out at you as being correct. So that's been posted at 8 o'clock tomorrow morning. All right, well, our goal this week is to talk about algorithms. And we talk about algorithms in 120 and 121 and 224, and I keep talking about algorithms versus code. And an algorithm is just a description of how you want to solve a problem, right? So if you want to find whether or not a number is prime, your algorithm is see if your number is divisible by 2 or 3 or 4 or any number up to the square root or half the number and minus 1 or something. And if it is divisible, return immediately and say it's not prime. If you try dividing it by all numbers and you don't find a divisor, then you can return and say it is prime. Okay, that's a algorithm for testing primality. So I know that you can all write algorithms to do different functions. What we want to look at today is different styles of algorithms, different classes of algorithms, because algorithms fall into some very broad categories. One which is going to be brute force, which is what we most usually go to. But other things, divide and conquer, dynamic programming, greedy algorithms. These are all different algorithms with different characteristics that have certain things in common. And I want to look at some different versions of algorithms for solving some problems. And we're heading up to a problem called the knapsack problem. And it's going to be the 0-1 unlimited knapsack problem. There's a lot of variations on it. This is going to be your 5th and final programming assignment. So we'll go through the details of that on Wednesday. But that's a problem which is best solved with something called dynamic programming. It's a style of algorithm that we're going to talk about today and Wednesday. But I want to start with a few sample problems and look at different styles of algorithms, brute force, divide and conquer, and so on, and see if we can get a feeling for the differences and commonalities of these approaches. Now this is for me, this was an entire semester-long course when I was an undergrad in computer science, right? It's a huge subject, that also includes things like proving the correctness of these algorithms, proving how efficient or inefficient these algorithms are, and so on. And we're just going to touch on this very, very superficially because we've only got 1 week really to do all of this. But you'll encounter these concepts again down the road. All right, so let's start with a sample problem. So this is called the maximum subarray sum. And we're just going to call it MSS. So here's the idea. Set of integers. And the question is, this is an array of integers. If we pick some subarray of integers, and we add those together, we get a number. So 6 plus 5 is 11, minus 3 is 8. If we pick this subarray, minus 1 plus 10 is 9, plus 2 is 11. If we pick this subarray, 4 minus 1 is 3, plus 6 is 9, plus 5 is 14. So we get a different sum depending on where we decide to start and end our subarray. And the question is, what's the largest subarray sum that we can get from this original array? And if you stare at it and you do some of the wonderful things that our brains can do, you can probably find an answer. And you can probably find some tricks that you're using along the way. For example, we know negatives are undesirable. So I mean, if I leave out this minus 1, I'm going to get a bigger sum with just the 10 and the 2. If I pick up the minus 1 and the minus 3, that's going to bring my sum down. But right here, I'm going to pick up 5. Right? That's pretty good. And I'm pretty sure my sum wants to have that 10 because 10 is so much bigger than most of these other numbers. But it's kind of a touchy-feely thing to try to figure out what the maximum possible subarray sum is here.
Is the entire array a subarray?
Yes, it is. Is that our largest? Yeah, that might be right. So in general, this is kind of a quirky problem. And we'd like to write we'd like to write some code to solve this. So we'd like to write a maximum subarray sum function. So something like MSS of array and some number n. Well, so how would we write code for this? Any ideas? This would be a great ODP. Or how could we do this ourselves systematically? Forget about the computer.
Have 2 pointers that point to, or 2 indexes rather, that point to the first and last.
Okay. All right, I'll get my blue and green indexes. So I can point to a first and last. And what do? We just add up the elements between those 2 indexes. That's the sum of that particular subarray, right? And if my indexes look like this, right, that would give me the sum of that subarray. And the goal is to iterate over all possible subarrays. Well, my blue index should cover every possible value, and my green index should cover every possible value, starting with the blue, because we could have a subarray of just length 1, and going out to the last entry. So if my blue index is right here, this is a subarray, this is another, this is another, this is another, this is another, this is another. Does that make sense? So I want to iterate my blue index from the first element to the last. And I want to iterate my green index from the blue index to the last. And I want to add up all the elements between the blue and the green and see what the sum is. And each time I do this, I'll just record what the largest sum is that I've gotten. And at the end of those two loops, I've got my maximum sum. So we could do something like for I equals 0 to n, for j equals I to n, sum everything from I to j. If s is bigger than the max sum, set the max sum equal to s. We're going to be writing a lot of pseudocode this week, so I'm going to ask you not to get bogged down on details. For example, if my array contains n elements, my index should go from 0 to n minus 1. I'm not going to worry about details like that for the most part, okay, because I don't want you to see an n minus 1 and start going down the path of trying to figure out why there's an n minus 1 for n elements and so on. So this is pseudocode, okay? So basically we're iterating over all the elements, we're iterating over every element from that first element to the end, and we're adding the sum of all the elements in between. And if it's bigger than the maximum we found, then that's our new maximum, right? Similarly, I did not initialize max sum to something up here. Don't worry about that. Okay, this is just an algorithm we're trying to capture. So this is an example of what we call a brute force algorithm. It's just muscling our way through basically all the possible cases. That's typically what we're doing in a brute force approach. Brute force algorithms are pretty easy to come up with for the most part because I think our minds are really good at coming up with brute force approaches. This is how we do things first order, right? We just kind of like jump into it and we start doing whatever our understanding of the problem calls for us to do. I don't know why brute force comes first. But to me, it feels like that's possibly the most natural algorithm that we tend to come up with, right? Just sort of break the problem into as many possible cases as we can find in some systematic way. So how much time does this kind of algorithm take, do you think? Order of complexity. It's pretty much going to be order n squared. Why is that? Yeah, we're going over some sort of loop here n times. It gets shorter, but it's roughly n times. And we're going over this outer loop n times. That's basically n squared. Maybe it's n cubed if we count the process of adding up the elements in the array. But the main factor here is the fact that we've got a pair of nested loops. Right, so this is order n squared. That's not horrible, okay? It's not like factorial or exponential, but it's not great. That's bubble sort efficiency. Okay, it's livable, but if you had a really, really big array, n squared can be pretty bad. All right, increase your array by 1,000x and your computation time goes up by 1,000,000x. Right, that's the sense in which n squared is less than desirable. But that's a brute force approach. A second approach is something we call divide and conquer. And it's just like what it sounds like. We take a problem we're trying to solve, we split it into two pieces, we divide it, we solve those two smaller pieces, and then we somehow combine those solutions. Okay, this is a classic algorithmic approach. This is how I sort your tests when I have to put them into Canvas. I've got a pile of tests and then I need to like enter grades. It's faster for me to have a sorted pile of tests than to flip back and forth through Canvas with the mouse repeatedly, right? So how do I sort 50 papers alphabetically? Typically what I do is I split it into two piles. I sort this pile because I can sort 25 papers pretty quickly. I sort this pile because that's another 25. And then I just pull off from the top of each pile in alphabetical order. So I basically interleave those two piles to get my stack of 50 sorted. Okay, that's a divide and conquer. That's also something called a merge sort. We'll talk about that later. But that's a divide and conquer. Break your problem into subproblems solve each of those, and then combine your solutions. So let's look at a divide and conquer approach to this maximum subarray sum question. All right, so here's 16 numbers, and we want to find the maximum subarray. Here's the first idea. Split it into two arrays of length 8. Find the maximum subarray over here, find the maximum subarray over here. How do we do that? Because we're writing a maximum subarray sum function. So call this function on this smaller array, get the maximum subarray sum from there. Call this function again on this subarray, get the maximum subarray sum. And if the maximum sum over here is 5 and the maximum sum over here is 15, right, then if we can find a subarray in here that adds up to 15, we can find a subarray in the entire original array that adds up to 15. So we're almost done. With one detail. What's the edge case here? We might have a larger one in the overlap. But we can name 3 cases. So step 1, find maximum subarray sum of the left half. Case 2, find the maximum subarray sum of the right half. 3, find the maximum subarray sum that touches both halves. And then just return the maximum of these. Okay, how do we find the maximum subarray sum of the left half? Just recurse. Just call MSS, pass it the left half of the array. How do we find the maximum subarray sum of the right half? Recurse. Call MSS with the right half of the array. So the only work we have to do is for this third case, where the actual maximum subarray comes from both halves. Well, if that's the case, we know that it contains this element and it contains this element. So we can break this into 2 substeps. So find the maximum subarray sum of first half. That includes the last element. And then find the maximum subarray sum of the second half. That includes the first element. Right, because if this purple array is going to give us the maximum sum, it's going to be a combination of some subarray that ends at the last element here and some other subarray that begins at the first element on the right half. And if we find the maximum sum here and the maximum here, and we just add them together, that's our maximum subarray sum that crosses the middle. So how do we do this? How do we find the maximum subarray sum from this left half that includes this last element here? What kind of algorithm could we use? So let me give you some numbers. Let's say this is our first half. We want to find the maximum subarray sum that ends with this -3. Well, what are the possibilities? What are the subarrays over here that end with -3? Yeah, so it could just be -3, it could be -1, -3, it could be 2, -1, -3, or it could be 4, 2, -1, -3. We can brute force this. And it's going to take us order n operations. So we're looking for a subarray here that includes this -3. If the array is only the element -3, that adds up to -3. If it includes the -1, that adds up to -4. If it includes the 2, that adds up to -2. And if it includes the 4, that adds up to 2. What's the largest value here? 2. So the maximum subarray that ends with the -3 is all of this stuff. So these, we can do brute force. And it takes roughly order n operations to do that third step. And that's the only real work we're doing in this MSS routine. We make a pair of recursive calls, and then we do an order n calculation.
How do you know what the bounds are for the middle set?
Pick a middle. If it's not, if it's an odd number, just pick left or right side of the middle point. And it doesn't really matter where we do this. We could do this anywhere that we wanted, but if we pick a point close to the middle, what happens is these recursive calls will work on something which is half as big as the original array. And that's going to involve making some recursive calls, which will work on arrays that are half as big as the array they started with, which is a quarter the size of the original array. So each time that we recurse, we're cutting our problem size in half. And we're going to need a base case here. Which is if our array contains only a single element, that's the maximum subarray. Right, because our subarray can't be empty. So if we pass an array containing a single number and we say, what's the largest subarray sum in here? It's just that number. So how many times can we cut something in half until we end up with a length of 1? Say we start with an array of n elements, how many times can we have it? Log n, there you go. This is why this dividing in half, whether we're doing tree operations or we're doing a divide and conquer, this is what makes it so compelling, because when you cut a problem in half, you can only do that log n times until you get down to a single element. Right? This is why high-low works well for searching, because you cut your problem space in half each time that you make a guess. So we recurse log n times, and at each stage we have to do roughly order n operations. This whole divide and conquer approach is roughly order n log n complexity, which is much better than n squared. Right? If n goes up by 1,000,000x, n squared goes up by 1 trillion. If n goes up by 1,000,000x, n log n goes up by about 30 million, 20 million, which is a whole lot better than 1 trillion. So n log n is nice. It's not as good as n, but it's more efficient than n squared. Okay, so that's an example of divide and conquer approach. Same problem, fundamentally different tactic for finding the solution. So let's look at dynamic programming. So the idea of dynamic programming is to take a problem and express its solution in terms of subproblems. Take a problem and break it into smaller tasks. Solve those smaller tasks and get your solution out of that. It's kind of like divide and conquer in that way, but we're not strictly just dividing things in half and putting together the two half solutions. It's a more general idea of taking a problem and breaking it into subproblems, where their subproblems are easier to do. Find the solutions to those, put them together to get the solution to the original, more complex problem. So we've got some numbers in our array. Okay, if our subarray is required to end with this first number, what's the maximum subarray sum? It's Monday, I know. It's just this number, right? Because our subarray is going to end with the first number. That's the only number in our subarray, and the sum of an array of one element is just that element. But if our number is going to end with this second element in the array, right? So we're going to make a subarray. We don't know what it's going to include, but we know it's going to include this element, and that's going to be the last element in the subarray. What are the possibilities for the subarray? Yeah, so it's got to include the second number, so it can't be just the first number. But it could be both of these numbers, or it could be just that second number. How do we know which one we're going to pick? Whichever one gives us the largest sum. So if we could compute the sum of the largest sum that ends with this number, and then add this number to it, that's the largest sum that ends with this number and includes this one. And if we don't include this first number, the largest sum is just that value itself. Okay, we can generalize this. So here's element I. And we want the largest sum, largest subarray sum. What was I calling this before? Maximum subarray sum. That ends with and includes element I. Okay, we're trying to find the maximum subarray sum that ends with this element I. Okay, so this has got to be part of the subarray. And these subarrays are continuous, right? So if we start here, it's got to be all the elements from there to the end. We want to find the largest subarray sum that includes this I. There's really only two possibilities. The first possibility is that if we find the largest subarray sum that goes up to here, we get a positive number. And if that's the case, if we take that largest subarray sum and we also include this number, we're going to get something bigger than just this number because we're adding something positive to it. But if the largest subarray sum that goes up to here is negative, and we add it to this number, we're going to get something smaller than this number because we're adding something negative. In that case, our maximum subarray sum ending here would be just this one element. In the first case, it would be whatever the maximum sum is that ends here, plus this one more element thrown in. So these algorithms are classic head scratchers, right? You really got to kind of be gentle with yourself trying to grasp this. But let's go through an example and think about all this and see how this plays out. So let me give you a sequence. So here's 9 numbers. All right. Suppose I require that my subsequence ends right here and includes this number. There's only one subarray in here that ends with this -2 and includes the -2. That's just the array containing -2. And the sum of all the elements in that array is just -2. So if we require our sequence to end and include this number, our maximum subarray sum is -2. Everybody okay with that? Okay, suppose I want a maximum subarray sequence that includes and ends with this number 1. There's two possibilities. I can take the maximum sequence that ends with this -2 and then tack a 1 on the end, or I could say it's just going to be the number 1. Those are the only possibilities, right? If I take the -2 and I add a 1, I get -1. If I ignore everything that comes before this and I just take this number, I get a +1. Positive 1's bigger. So my maximum subarray sum at this point is 1. Okay, suppose I want a subsequence that ends with this -3. Again, there's two possibilities. I can just take the -3 by itself, which gives me a sum of -3, or I can add some numbers that come before it, right? The largest sum that I can get of numbers that come before it, we already found. It's 1. So if I take that subarray and I add a -3 to it, I'm going to get 1 minus 3 is -2. That's bigger than -3. So my maximum subarray sum up to this point is -2. And we can keep doing this. At each point, we're going to take either this number or this number plus the maximum sum that ended right before it. Whichever of those is bigger, that's our maximum. So we've got 4 versus 4 minus 2. Which one's bigger? 4. Here we've got -1 versus 4 plus -1 is 3. 3 is bigger. Here we've got 2 versus 3 plus 2 is 5. 5 is bigger. Here's a 1 versus 5 plus 1 is 6. 6 is bigger. Here's -5 versus 6 plus -5 is 1. 1 is bigger. And here's a 4 versus 1 plus 4 is 5. 5 is bigger. Those are all the possible maximum subarray sums ending at each of these positions. So what's our maximum value out of all of this? 6. That's your maximum subarray sum. And that's order n. Okay, so what's going on here? We're breaking this problem into subproblems. And each subproblem we can solve by taking a subproblem of that and performing some operation on its solution. For example, to find the maximum subarray that ends with -1, we need to know what the maximum subarray is from all of this that ends with a +4. And that turned out to be 4. And so the maximum subarray that ends here is either just this number or this number plus some stuff that came before it. And the biggest sum we can get of the stuff that comes before it is 4. So if we take that stuff and we add a -1, we get 3. If we just take a -1, we get -1. So we know the maximum subarray up to here is 3. And we keep building like that. So what's the algorithm here? So the maximum subarray sum that ends at position I is equal to either the element at position I or the maximum subarray sum up to the I minus first element plus the ith element. And it's the largest of these. That's really all we're doing. And this is how all our dynamic programming stuff is going to look at some level. We're going to try to find a solution to some problem with size I. And we're going to find that if we can solve the problem for something smaller than I, we can do something with that solution and get a solution to the original problem of size I. All right, let that percolate for a bit, and let's look at a different problem. So this is called the longest common subsequence. So here's the idea. We've got two strings. Here's one string. Here's a second string. And we'd like to find a collection of letters, not necessarily consecutive, but in the same order as in the original string. We want to find a sequence of letters that's common to both of these strings. For example, here's an ADH, here's an ADH. They're not in the same positions, they have other stuff in between, but this substring, this subsequence ADH is found in both of these original strings. And we'd like to know what the longest common subsequence is. And we can kind of brute force it with short strings by just looking at it. But our question is to come up with an algorithm for doing this. And this is a real world problem. Okay, so Roberto upstairs, he's doing some gene sequencing. And he has this great little device. You plug it into a USB port, and you put a sample in it. And it basically takes DNA and splits it in half and sucks it through these tiny little nanoscale pores and runs electric current through them, and based on what's the chemical composition is, ACGT, you get different electrical field disturbances, and you can tell what the base pairs are as this thing comes through a nanopore. And there's 1,000 nanopores in this object, so it's splitting and sequencing 1,000 strands of DNA in parallel. And when you're done, you get things like this, Gattaca, right? So 4 letters. And one of the things you want to do is you want to piece these things together. You want to know that this part of this strand is actually the same as this part of this strand, so you can line them up and you can put these individual strands together and get a long sequence for the entire genome. And his CPU runs for days doing this, right? It's a hugely complex computational problem, but it's a classic piece of this sequencing operation. So what's a brute force approach to this? Well, we could pick a subsequence from here and see if it's contained in here. So suppose I pick my subsequence ABC. I go through here, I look for an A. As soon as I find it, I continue looking for a B. If I find a B, then I continue looking for a C, right? And if I don't find one of the letters I'm looking for, I know the subsequence isn't in here. And I simply do that over all possible subsequences of this string. Now, how many subsequences are there? Too many. Think of this as a set. Ignore the fact that we might have an element occurring more than once. If this is a set of elements, a subsequence is just a subset. And how many subsets do we have in a set of length n? Right? That's the good old power set. So there's 2 to the n subsequences, right? And we can do this by simply taking a binary number of n bits for n characters, and a 1 means that we're going to include that letter in our subsequence, a 0 means we're not going to include it. And each subsequence corresponds to an n-bit number, and we have 2 to the n possible n-bit numbers. So we have 2 to the n subsequences, and for each of those, we need to march through these n or m characters and match up. So this is something like, order m times 2 to the n. And the 2 to the n is the critical part. That's what really kills our performance. Right, so if you increase the amount of data by 64, this problem goes up by 2 to the 64th in terms of time complexity, which is a ridiculous number. It's like 10 to the 20th or something, right? Just for 64 times as much data. So a string of length 1,000 versus a string of length 20 takes a billion, 1,000 times more. All right, so order 2 to the n is horrible complexity, right? It's not where we want to be. So there's a dynamic programming algorithm we can use to solve LCS. And it's based on the following. Two possibilities. It could be that our 2 sequences, our 2 original strings, have a different last character. Or it could be that our 2 original strings have the same last character. Okay, remember a subsequence is any collection of characters from the string. They don't have to be consecutive. Okay, they just have to be in the same order that they appear in the original string. If we know that both of our strings end with the same letter, whatever letter that is, X, Y, W, whatever, right? If they end with the same letter, we can break this into a smaller problem. If we can find the longest common subsequence of these 2 strings by simply adding the letter X to the end of each of those common strings, we get a common string between our 2 original strings. Because if both of these strings end with the same letter, we can take a common sequence from this and just tack this last letter onto the end of each, and we still have a common string between our 2 originals. So in this case, so let's name our strings m and n, and let's give it a length of m, little m letters and little n letters. And let's find the least common subsequence of string m with length m and string n with length little n. And if m and n have the same last letter, so if m bracket m equals n bracket n, we simply need to find the longest common subsequence in the first m-1 characters of m and the first n-1 characters of n, and then add 1 to it. So think about why this makes sense, if it makes sense. Let's say that our strings are A, B, C, G, H, J, and A, D, C, F, G, J. All right, what we're claiming is that if you find the longest common subsequence between these, we can add a j to the end of that and find a common subsequence between these. And that should absolutely work. So what's the longest common subsequence between these things in the blue circle, A, B, C, G, H, and A, D, C, F, G? ACG. And so the longest common subsequence between these purple ones will be ACG with a J. Right? Because anything that's in common between these and these, if it's the longest one, it's going to have to include that J at the end. And if we ignore the J, it's going to be some sequence that's in common between those two prefixes. So this part is pretty straightforward, right? If the last letters agree, find the longest common subsequence in the earlier pieces of those strings and then just add 1 to it to say that we're tacking on that last letter. But suppose the last letters differ. So suppose we've got this A, B, C, D, G, H, and A, E, D, F, H, R. So this last letter is not the same. So the longest common subsequence between here and here is not going to include the H and the R, right? So this part's a little tricky. But if we find the longest common subsequence of these two strings, right, ignoring that R on the second string, and we find the longest common subsequence of these two strings, one of those will be our longest common subsequence of these two original strings. Why is that? Because it could be that our longest common subsequence ends with an H, in which case it's not going to include this R. Or it could be that it ends with an R, in which case it's not going to include this H. Or it could be that it ends with neither the R or the H, in which case it's still going to be the longest common subsequence of these two strings or these two strings. So we have another possibility. If the last letters don't agree, then return the largest of the longest common subsequence of m, little m, n, n minus 1, and longest common subsequence of m, little m minus 1, n, and little n. Right, and that's coding this idea that we want to find the longest common subsequence in these two cases. And all three of these problems, this one, and this one, are smaller than our original problem. Because at least m or n, or maybe both, are smaller than our original m and n. Right, what we're trying to do here is solve this problem. And we need to do a recursive call on something that's slightly simpler. So this is a few lines of code if you do it recursively, right? If the last letters are the same, just find LCS of m minus 1, n minus 1, add 1 to that answer and return that. Otherwise, find these two longest common subsequences, take whatever the largest answer is and return that. Okay, classic dynamic programming. And in both of these cases, you may be wondering, we haven't actually found what the subsequence is. Okay, we're just finding the largest value. There's some housekeeping you have to do if you want to actually know how you got to that maximum value. But for the sake of figuring out the dynamic programming part, right, we're just finding what the largest sum is or what the longest subsequence is. But it would be pretty easy to have this thing return the positions of the elements or the binary number corresponding to that maximum subsequence. All right, let's take a 5-minute break, and then we'll go on to a more concrete problem.